Hi everybody, welcome back. So this time we're going through dimensions and units. Woo-woo! Okay, now I'm not talking like other dimensions, like alternate dimensions, like we're going like in Marvel here. Dimensions in physics is actually a lot less interesting in a way, or really cool, depending on who you are. So just think about it this way: the entire physical world, we can describe it, we can measure it. However, we're going to talk about that, we need to have some sort of consistent set of terminology. So this takes the form of dimensions and units. Let me move my head out of the way. There we go. So dimensions are a concept. They're an idea. You can qualitatively describe them or compare them just by themselves, but you can't, dimensions are not a measurement. Like if I go outside, well, you're like, whoo, it is hot out there. I'm describing temperature. Temperature is a dimension. And I can qualitatively describe it just by itself saying it is hot. The temperature today is hot. Yesterday it was cooler, but hot and cool, they mean different things to different people. If you're from Alaska, hot might be like, it is 55 out there. I am melting. If you are from Florida, it is 55 out there. I'm freezing to death. And if you're from, Europe, it's 55 out there. I'm scared to leave my house. They do use Celsius. It's a joke. Okay, terrible teacher joke. Continuing on. So units. Units are how you measure dimensions. They're a set quantitative amount of a specific dimension, and they're unambiguous. The temperature is 98 degrees Fahrenheit today. Well, that is indeed hot for most people. Maybe it's cool for somebody. I feel sorry for you, person. But you know what 98 degrees Fahrenheit is. If I say it was 65 degrees Fahrenheit yesterday, I don't have to tell you it was hotter or colder. You know 65 is less than 98. Therefore, it was cooler yesterday. So it's a measurement, okay? It's a quantitative measurement. So units, quantitative, they have numbers. Dimensions are a concept that we can qualitatively describe, okay? So if it doesn't have a number attached to it, it's not a unit. And I've stuck there. There we go. Okay. So let's jump into some of these units and dimensions. Again, too big for my whole spot here. I'll move myself right there. Okay. So L equals length. I'm using these little symbols on purpose. I know you know that length starts with L. But there's sometimes where I use something called dimensional analysis. We don't do it too much in this class. However, your book does it. It's a somewhat okay skill to have. Okay, but dimensional analysis, we'll get to that eventually. We're not there yet. This is just introducing them. So length describes distance. You know that. We use words like far away. It's a short distance. It's very tall. It's very long. Those words can describe it. And you can say it is longer, it is taller, but that isn't quantitative, that's qualitative. So length is the dimension, it's the concept, it's the idea. Now, how do we measure it? Well, there's actually 3 units of measurements. 99% of the world uses metric. Okay, I say 99, it's not quite 99%. There are 3 countries who do not use the metric system, which is also known as the SI system. Those are the United States of America, and there's 2 countries in Africa who use it as well. Everybody should use metric. Okay, I'm going to go out there and say that I like the metric system. Makes a lot more sense. But that's okay. The United States has 2 different systems, the USCS and the AES, okay? AES is the American Engineering Standard, and the USCS is terrible. Sorry, I mean United States Customary System. It's also terrible. Find out why later. Okay. So when we're measuring distance, we use either meters or feet. You're like, what about miles, yards? There's other things. You're right, but these are the base units. Yards are made of feet. Miles are made of feet. You're like, what about inches? Inches make up feet. You're correct. You're correct. However, more people use feet, and so that's our basic thing. So we're saying that an inch is a fraction of a foot, rather than the foot is 12 inches. Okay, it's semantics. I get it. It's just whatever you use the most, you use that to describe things. Like if you're an astronomer, you don't use feet because the number of feet to the sun is immense. The number of feet to the nearest star besides our sun is humongous. It's gigantic. So they use light years because that's the best unit for them. So their standard unit is a light year, not a foot or a yard or a mile. Just depends on who you are. Okay, so little fun tidbits here. The meter is actually based on the distance light travels in 1/299,792,458 of a second in a vacuum. Where this is actually the speed of light in a vacuum, meters per second. That's how it's defined. Okay, and then feet. Feet were originally actually based on the actual size of the king's foot, and it actually changed with each king until eventually realized this is a bad idea to keep on changing this measurement. Let's make one standard measurement for it. But it's easy to understand. Like a foot is roughly the size of most people's feet. Now, if you've got tiny feet, it probably doesn't work for you, but on average, it's kind of close. So it's a little easier to see in that way. Okay, mass. Mass is like, well, it's how much I weigh. No, it's not. Your weight is actually a force. It's how hard gravity is pulling on you because of your mass. Mass is actually how difficult is something to move or accelerate. That's the best way to measure mass. Because I know this is going to be kind of crazy for you. But if you look at like quantum physics, this is kind of crazy. And you look down to the smallest particles, like you're thinking like electrons, protons, smaller than that. Because what keeps a proton and a neutron together? I think it's called a gluon. Yeah, I'm almost certain it's called a gluon. And it actually has more mass than the atom. Your minds are blown. You're like, what? That doesn't work. It does, because mass is just how difficult is something to accelerate. And these little gluons that hold protons and neutrons together, they're incredibly massive because they're very difficult to move. They can only move from a proton to a neutron. They can't move any further than that. They're very, very, very hard to move. They actually have more mass than an entire iron atom. One gluon. Crazy. Okay, so I know your minds are kind of blown right now, but just remember it's how difficult it's something to move, because if you're in space, you have no weight. There's no gravity pulling on you. You have no weight. However, if you weigh if you have a mass of 15 quadrillion kilograms, a little dinky rocket's not going to accelerate you all that fast. It's going to take it a long time to get you going. It will eventually. There's nothing slowing you down. It's going to take a long time to get you going. If you weigh half a kilogram, the little dinky rocket's going to accelerate you really quickly. You're just going to get going like nobody's business. So in either way you move, it's just in one case you're easier to move. So mass, how difficult is something to accelerate? Okay, in metric system they used a kilogram, which is actually, well, originally it was based on the mass of 1 liter of water. Now it's based on a bunch of physical constants of the universe, which is kind of crazy and cool at the same time. And the pound mass is the USCS unit of mass, and it's terrible. I'm just going to skip it for a second and go on to the good one. And then the AES, the American Engineering Standard, has the slug. Okay, so that's pound mass for the USCS. AES is the slug. Pound mass is a bad unit. Reason? It only exists because most people in the United States of America didn't know the difference between weight and mass. Maybe you didn't before today. And so if you asked them what their mass was, they would give you their weight. They would say, oh, 155 pounds. If you asked them what their weight was, they would say the same thing, 155 pounds. Not the same thing. They're completely different quantities. And so we eventually just said, well, let's just make a system of units where 1 pound mass has a weight of 1 pound force. And this works on Earth and only on Earth. So if you see pound mass in a problem, don't use it, convert to kilograms, and then do your problem. There are only a few times where it is actually helpful. Most of the time it will just mess you up. So pound mass is a bad unit. Avoid it at all costs. Slug actually works just like a kilogram does for the AES system. But just going to make it right now, don't use pound mass. It will mess you up. Okay, with that, kind of a little bit of an intro into what dimensions are and into what the units are. And next time we'll jump into them a little bit more. See you later. Bye-bye.